Hi, my name is Derek Whippler. I'm a dev on the pipeline team here at Milken, and I want to share with you a short story of how and why we rewrote our outbound SMTP server in a matter of months. To understand why we rewrote our SMTP server stack, you have to understand a little bit of where we came from and what we have. In the beginning, there was a load balancer, Nginx, and Python. At the ELB level, both Nginx and ELB provided load balancing for the upstream Python servers. It was kind of a redundant system. In addition, the mail SSL module terminated the TLS. This was to simplify the upstream SMTP server written in Python. Python could focus on the work of processing the MIMEs and sending off the emails, and Nginx could worry about securing the connection. There are two ways to begin a TLS conversation as SMTP. One is preemptively, and the other is using the start TLS command. The Nginx module here is smart enough to handle both. So moving down the stack, the Python SMTP server consisted of many instances of the interpreter because of the GIL in Python. The best way to get a lot of concurrency when doing CPU work like parsing a MIME is to run many, many interpreters. And at reasonable scale, this really isn't a big issue, but as we continue to scale to billions of emails a day, this was going to be problematic. One of the problems is that you have to throw more and more resources at the servers to get them to scale. With an interpreter taking up a minimum of 60 megabytes per interpreter, doesn't sound too bad, but when you run a minimum of 20 instances of those interpreters, the memory that could otherwise be used for the application is being used by the interpreter, and that has diminishing returns as we continue to grow. The other issue here is that this implementation loaded the entire MIME into memory. So if we had thousands of 25 megabyte MIMEs sent to us simultaneously, the interpreters would grab all the memory out of the box and then crash. We could rewrite the Python server in Python to avoid this, but the team recently had great success with Golang. Golang has built-in support for high concurrency without the limitations of the GIL and without the overhead of running many instances on the server. You can run a single Golang server on the box, and it will scale to utilize all the available CPU and memory as needed. This means we can accept many more concurrent connections on a single box than was previously possible with Python. Also, it's new and shiny, and who doesn't like the new and shiny? Also, it simplified our architecture and gives us on-the-wire introspection of what our customers were actually doing. Because remember, part of the SMTP conversation was in Nginx, and the other part was in Python. The greeting would occur, and the start TLS calls were all handled inside Nginx. And with Golang, we would have full control and understanding of the connection and TLS conversation. But this was all going to be future work. This was a one day when we had time and nothing else was pressing. Until this guy comes along. Patronics wanted to send 3 million emails per hour, which is about 833 emails per second. And their initial tests against our current architecture wasn't performing. While attempting to send millions of emails, they would get random timeouts and were generally unhappy with the performance our server was providing. Again, because of our current architecture, we had trouble understanding the problem. As part of the conversation was happening in Nginx, the other half was in Python. The Python side would look okay, but Patronics would report timeouts. Normally, this wouldn't have been a big cause for concern. We would have just adjusted customer expectations, right? Except Patronics had the potential to send a lot of money our way, and honestly, we really needed to be able to court bigger companies with bigger sends, but that had much more demanding performance characteristics. So Maxim says to David, in a month we can have a working prototype, good enough for the Patronics use case. So David gave him a green light. And in a week, Maxim had a prototype that was able to accept messages. So our dream of Golang became a reality, and we sang and we danced. The end, right? Not really. We had our shiny new stack, but we still didn't have the performance that we wanted. And Paytronix was still reporting random connection issues. So now that we had greater introspection into what the customers and turns out non-customers were doing with our servers, we noticed a good deal of random people on the internet connecting, disconnecting to our servers, sending random garbage, and generally just making a nuisance of themselves. To simulate this random connect-disconnect behavior, we wrote a program called Hammer, which would connect and disconnect and also send email. And we ran it at very high concurrency. When we did this, we noticed the random connection issues that customers were reporting. Lower connection rates didn't really have an issue, so whatever was happening was only appeared to happen when we were accepting a high volume of new connections. To understand what was going on, we need to talk a little bit about how servers work in general. In Nginx, as in our implementation of Influx, there's a single thread worker that listens for incoming connections and passes that connection off to a pool of workers who then work the connection. What we discovered was that when the incoming connection rate had saturated all of our existing workers in the pool, we were unable to spawn enough new workers to keep up with the incoming demand. So while Nginx had a predetermined number of workers, which was configurable on startup, Influx was dynamically adding new workers as needed. But in practice, we found that this wasn't sufficient to keep up with the incoming demand for new connections. This caused the listen accept worker to block and to no longer accept incoming connections. As such, clients would see a timeout connect. At first glance, the solution might appear to be just to increase the number of workers in the pool. But we had memory limitations, and if we had an unlimited number of workers, Influx would eventually consume all the memory on the box and crash. The solution we came up with was to have a second pool of workers on standby, which would handle the overflow. In this scenario, the disposer's only job was to inform the client the server was overloaded and disconnect the client. So now when the worker pool was busy, clients wouldn't get a connect timeout. They would instead get they would instead be told to retry again later. After implementing this, our connect issues while using Hammer went away completely. However, after we deployed this, Paytronix was still reporting issues. This is when we started looking at SYN drops, and this here is a screenshot of a TCP dump that the customer sent us. A SYN, to understand this problem, a SYN is at the beginning of a TCP conversation, the handshake, if you will. Ideally, the server would respond back with a SYN ACK when it receives a SYN, and the connection handshake would be complete. We'd have a brand new connection. But inside the kernel, the TCP IP stack, there are several queues and buffers which control how connections are handled. Particularly here, there is a SYN queue, which handles all the incoming SYN requests for new handshakes. But what happens if this queue is full? We have all these SYNs received by the kernel, but where do they go? Well, the kernel, it turns out, silently drops these SYN requests, and thus not completing the TCP handshake. And from the client side, the connection never connects and usually ends up, from their point of view, looking like a connection timeout. The simple answer to this problem might be to just increase the SYN queue, and while that did help, Constantine found that when we disabled the TCP reuse feature of the kernel, most of our lingering SYN drop issues went away. By the way, Constantine did an amazing job of analyzing the kernel to solve this issue. He wrote up a very detailed analysis of the changes he made and how he came to his conclusions. If you want a copy of that, I'm sure if you reach out to him, he can provide you with a copy. And as you can see in this chart, the number of SYN drops dramatically dropped after we deployed this change. So what about performance after moving to Influx? Remember, our target was 3 million emails an hour. Our testing yielded a huge increase in throughput when sending thousands of emails concurrently, which was way above the 3 million an hour Patronix was targeting. The massive amount of currency that we were able to achieve was made possible in part by our switch to Golang and the capabilities that it provides. But Golang wasn't without its own problems. For the first time ever, we had problems with the garbage collector during high volume sends, with the GC stopping the world for over 1 second in many cases, and averaging GC runs would run way above 300 milliseconds. You can also see in this chart that we were using a ton of memory. So to understand what we did to fix this memory problem, we have to talk a little bit about MIME parsing. Our initial naive implementation of the server followed in the footsteps of the Python version, which loaded the entire MIME into memory. This is problematic, as if users send a ton of 25 megabyte MIMEs, Influx can, like the Python version, quickly consume all the memory on the box and crash. To fix this, we designed the Golang version of our MIME parser to be streamable from day one, such that only the minimum required data was actually in memory. Everything else is immediately streamed to our data store called Buffer. When we were working on the MIME parser, we were able to reuse the tests and the test MIMEs that we had collected over the years from our Python implementation. So by the time we were ready to deploy the new MIME parser, we were feeling pretty darn confident that this implementation was going to handle anything the internet could throw at it. But when we deployed it, the MIME parser immediately panicked while parsing some of the garbage that our customers routinely sent to us. But we added some checks for that panic, and we're able to retrieve the MIMEs that caused the parser to panic and fall back to our previous parse without causing service interruption. What we found when inspecting those MIMEs was shocking, for me especially. There were corner cases that I had not even dreamed of that were possible, and exposed some rather nasty errors in the parser code. And as we were going through these MIMEs, we quickly realized that there were so many corner cases that trying to come up with a suite of tests that covered all the possibilities would take forever. So we ended up using a tool that we'd read about previously, but had never had the opportunity to use until now, and that was fuzz testing. Fuzz testing, in a nutshell, is controlled input to your application, which is randomly generated, such that the more iterations of random data you send to the API, the more likely you are to hit a corner case that exposes a problem with your code. So when we first wired this tester up to the MIME parser, we ran it, and I was rather disappointed we didn't find any errors. We ran it again with 10,000 iterations, still no errors. We ran it again with 20,000 iterations, still didn't find anything. It wasn't until 200,000 iterations that we actually hit our first corner case. So it really impressed upon me we need a lot of entropy to start hitting some of these rather obscure corner cases. We made a regression test covering the corner case we exposed. We ran it again, and we found another corner case. We ran it again, and we found another corner case. In all, we uncovered about 5 different corner cases that just normal testing probably would not have found. The result of all this work was that we had a streaming MIME parser, which significantly reduced our memory usage, and in turn allowed us to increase the number of workers in our pool. So remember those disposer workers, we could now reduce those to essentially just 1 or 2 sitting around waiting to tell somebody that the system is overloaded. But we have so much concurrency now because we can handle so many more MIMEs. We don't have to load them into memory, but that is almost not a problem anymore. And we can achieve such a great level of concurrency per server than was ever possible before. In addition, because we weren't loading everything into memory, the stop the world GC pauses were dramatically reduced. So, in conclusion, the results of our rewrite using Golang, we simplified our architecture. We gained a higher level of visibility into what our customers were doing and what was happening on the wire in the SMTP protocol. We achieved a lower memory footprint. We improved concurrency, and we improved our test coverage. And so thanks for listening, and I'm going to stick around for some Q&A.